Welcome to everyone. This is a new class, and today's topic of discussion is work power energy. And this is a topic that you already know, and from class 9, I think it is from class 9. The most of the part of this topic actually is already is covered in class 9, and mainly the same topic we will discuss here also, but our discussion will be on mainly based on uh, differential approach, or by using differentiation, or mainly using calculus. Okay, so that will be a different approach, and that I will actually provide you a brief idea about a varying force, or any kind of displacement, or any kind of force that is time varying, or that is varying with position or displacement. Okay, so let's start. So now, what is work? As we know, when an object a force is applied on an object, and the object suffers a displacement in the direction of the application of the force, then a work is said to be done, and the amount of work that is done is actually given by this equation, that is W equals to Fs cos theta, where F is the force and S is the displacement, and theta is the angle between the direction of the force and the direction of the displacement. Okay, and so we can write this equation as F dot S, where that Fs cos theta can be represented as the dot product of force and displacement. As we know, A dot B is our AB cos theta. Okay, now it's already known to us, that is the SI unit of work is actually joule, and CGS unit of work is arc. Okay, and 1 joule is your 10 to the power 7 arc. Okay, now we can prove that, but for our class, for our actually syllabus, that is not very much important, so just we are okay with that value only. Okay, so next part of our discussion is actually based on the power. Now we already know what is work. Now what is power? Power is actually work done per unit time, that is the rate of doing work. Okay, that means it is actually defined as work done per unit time, that is total work divided by time. And as we know, this is work done is actually force into displacement, or precisely, that is force is and displacement both are the vector quantities, so precisely that is dot product between force and the displacement divided by the time. So this time is actually a scalar quantity, and it can operate on force as well as on displacement. Okay, so F dot, we can write this term is by t, and S by t, that is displacement by time, is our velocity, that is F dot v. That means the power is actually dot product between force and the velocity attained by the object due to the application of the force. Okay, now what is the unit of power? As we can see from the equation, that is the power is our work divided by time. Work is actually represented by joule and time is by second, so that means the unit of power in SI, that is joule per second, and it is termed as watt. Okay, so watt is actually your joule per second, or joule can be written as work multiplied by second. Joule can be written as work multiplied watt multiplied by the second. And why I am writing this? Because in later part of the discussion, actually we will going to use this equation. We are going to use this equation. So the another unitary system is CGS, and in that unitary system the unit is arc per second. Okay, so another term related with the chapter, as you can see, work, power, and third term is your energy. Now what is energy? Energy is ability to do work. So as you can understand, that is the ability to do work. That means that must have the dimension that must be same to the dimension of the work. So more or less these two terms is actually same, since both sounds different, but actually without having any kind of energy, we can't do the work. So that means work and energy, that is the synonymous. Okay, so that means what is the energy? That is ability to do work, and that means that has the dimension same to that of the work. So the unit of energy is also joule, sorry, that also joule, or CGS unit is arc. Okay, so actually that doesn't true for the all the time. Actually for heat we use calorie instead of joule. So that means energy can have the different units depending upon the name, or depending upon the functionality, or depending upon the characteristics of the energy, or where it is actually being applied. Now power, that is another. Now starting with the power, that is the energy divided by time. So that means the energy can be written as the power multiplied by time. Why I am writing this equation? Actually my main aim to find out the commercial unit of power, and the commercial unit of the power is found by using this equation, that is, sorry, commercial unit of energy is found by using these equations, that is the power multiplied by the time. So power is in watt and time is in minute, hour or second. So that means the commercial unit are watt hour, kilowatt hour. Okay, now what is watt hour? 1 watt hour energy is the amount of energy consumed by a machine that is rated with 1 watt. That means a machine that is actually that has the power of 1 watt, when it actually runs for 1 hour, the amount of energy that it consumes is the 1 watt hour energy. Okay, now from the equation we can write 1 watt hour, that means 1 watt is the power and time is 1 hour, and hour is our 3600 second. So that means on multiplying these two things, that will be 3600 watt second, and it is 3600 joule. So as I just mentioned, the watt into second is joule, and here is the equation that is the equation, and that means joule is our watt into second. So watt into second can be written as joule. Now what is kilowatt hour? That is the amount of energy consumed by a machine that is rated with 1 kilowatt power. That means the machine that has a power, that actually using a power of 1 kilowatt, when it runs for 1 hour, the amount of energy that it consumes is 1 kilowatt hour. Okay, and from the definition, that 1 kilowatt hour energy is the power multiplied by that time, that is 1 kilowatt multiplied by the 1 hour. That means 1000 watt multiplied 3600 second. Now just multiplying the two things, you will get that 3.6 into 10 to the 6 joule. So this is the relation between kilowatt hour and the joule. Now just keep one thing in your mind, that is this kilowatt hour is called sometimes board of trade unit, that is board of trade unit, that is BOT, and it is used by mainly CESC or any electric supply board, and the unit written in the electricity bill, that the consumed power, the consumed energy is 100 unit or 200 unit, that unit is actually 1 BOT or 1 kilowatt hour. Okay, so this is the thing. That means if you have our electricity bill of 100 unit, if you have consumed electrical energy of 100 unit, that means you have consumed 100 kilowatt hour amount of energy. That means 100 into 3.6 into 10 to the 6 joule, that much of energy you have consumed in 1 month. Okay, so that's all about the definitions and all about the introduction about this chapter. Now we will go just deep into these topics. Okay, now for our case, we will actually discuss or focus on our today's discussion mainly the mechanical energy. That is mainly two type of mechanical energy is there. One is kinetic energy, another one is potential energy, as you all know. Okay, So what is kinetic energy? Kinetic energy is the amount of energy that is actually possessed by the object due to its motion. Okay, and here I have shown some derivation, some kind of calculation that shows the amount of kinetic energy obtained by the object due to its motion or due to its velocity v. And let why first thing is that why an object gets some amount of energy due to its motion. Okay, now let's start with the basic assumption. Let's the object is at rest. Now due to application of force, now how this object actually gets the velocity? The simple reason is there must be a force on the object. So our assumption is the force that is applied on the object is F, and for that force the object actually gets the velocity v after time t. Okay, that means the object is under influence of a force, and after a certain time t it gets a value of its velocity which is the value to v. Okay, so that means that object must be displaced due to this application of this force. So that means some amount of work must have been done on the object, and that work actually is being stored in the object as the kinetic energy. Okay, so that is the thing. So that means the work done by the force is converted into the kinetic energy in the object. Okay, so the work done by the force that we can calculate as W equals to F into S, that is the force into displacement. Okay, now one thing again, this approach is completely analytical. Here I am not showing any kind of calculus or any kind of differentiation or integration here. So I will do that later, so you can understand. You will actually see the same derivation we will do again for the work energy theorem, and for that time we will focus or we will discuss on the basis of calculus or the differential approach. Okay, so mainly for that case our approach will be based on the calculus. Now for this discussion, just want to keep the thing simple, so this is only based on the some simple and analytical assumption. Okay, so let's do that. So that is force into displacement, and force can be written as mass into acceleration, so that will be your ma into s. Okay, now our motion of the object started from rest, and that got the velocity v after time t. So we can have a relation between initial velocity, final velocity, and the displacement, that is v square equals to u square plus 2as. Now my initial velocity is 0, that means v square equals to 0 square plus 2as. So as equals to v square by 2. Just by putting that as value of as here, you will get w equals to mv square by 2. That means the work that is done on the object by the application of the force is actually mv square by 2. So that means the object will get the same amount of energy, and it will be stored as the kinetic energy in the object. So the kinetic energy in the object will be half of mv square. Okay, if you find any kind of discrepancy or any kind of doubts, just note it down, and we will clear that. We will discuss on that in our next class. Okay, so next one is potential energy, and that is the energy stored an object due to its position or due to its shape or due to its size. Okay, so that is called potential energy. And the first thing is the potential energy that is due to the position due to the gravitational force, and that is actually can be explained here, can be explained by using this diagram. Now the object of mass m must have a weight of m into g that is actually directed towards down, and by this force this object will go down if it is at a certain height h. Okay, So now let assume the object is at the ground and the weight of the object is mg. Okay, now the object is at ground, weight and its weight is mg. Now we want to lift it up by an height h, to a height h. Okay, so that means the object will be lifted up to a height h. So that means the force is mg and displacement will be your h. So that means work done on the object will be force multiplied by the displacement, and that will be your force is mg and h is your displacement, that is mg multiplied by h, that is mgh. Okay, so that means this amount of work is done on the object. So that means the same amount of energy will be gained by the object. So the amount of potential energy gained by the object is the amount of work done on the object is equals to mgh. Okay, so this is an example where due to the position object gets some amount of energy. Now in our next discussion we will see the amount of change in the position, the amount of change in the size or shape, that also leads some amount of energy stored in the object. Okay, so let's start with a spring, and that has a length of L. Okay, and let it is elongated by a length of x. So initial length of the spring maybe this is L, and now this spring is elongated and by a length of x. Okay, so that means this one is x maybe. So this is the original length of the spring, and this is the next condition of the spring where it is elongated by a length of x, and again from that position again we actually applied a force and the spring is again elongated by a length of dx. Okay, now our assumption is this small displacement or small elongation dx will not need any kind of additional force. That means the elongation of x is merely due to any kind of application of force, obviously. So the spring is elongated by a length of x is due to a force F, and that force can actually elongate the length of the spring by additional length dx. So that is our assumption since dx is tends to 0. Okay, now as we know that now the spring, if you try to elongate it, the more amount of elongation do you want, you have to put more amount of force on it. Okay, so that means the amount of force you need to elongate the spring must be proportional to the length of the spring. So that means the amount of force needed to elongate a spring is directly proportional to the amount of elongation that we need. That means F is proportional to minus x. And why it is minus x? That means it is actually not applied force. That is the restoring force. That means when we release the spring, that actually comes back to its original shape. That the reason behind it, the restoring force. This is a force that always acts on the spring that actually want to restore the original shape or the size of the spring, and this is the reason the spring always comes back to its initial position or initial size. Okay, so that is the restoring force that always has a negative sign, since it always has a direction to its initial position, so it's negative. Okay, so amount of force is proportional to the amount of elongation that we need with the negative sign. So F is actually minus kx, and this is the restoring force. And as I just already mentioned that for the applied force, negative sign will not be there, so the amount of displacement, the elongation of the spring is by dx. So the work done on the spring will be the force into dx, that is F into dx, and F will be our kx dx. Okay, now here we are going to apply the calculus. Now this is the amount of work that is done on the spring to elongate the spring by a small amount of length dx. Now we want to know about the complete elongation, that means from 0 to x. 0 where when the elongation was 0, that means it was in its final initial condition, and when the elongation is x, that means it is its final condition. Okay, so we want to just find the amount of work done on the object for a elongation starting from 0 to x. So we have to integrate that. Integration actually gives you a value for a overall thing when you have the value for a small amount of changes. Okay, so that is the integration that actually can increase any value, or it can give a overall idea on the basis of a small amount of change. Okay, so you just have the idea of kx dx, that means a small value of dx, you know the amount of work done, and for the whole value of elongations from 0 to x, you can get the value of work done by just doing the integration over it. So this is the process. Now integration, when we do integration, the k is our constant, that is the proportionality constant, it will come out of the integration, and now so it will be our integration of 0 to x x dx. Okay, k is our k actually comes out of the integration. Now the main formula for integration that we are going to use here, that is x to the power n dx. Integration of x to the power n dx gives you x to the power n plus 1 by n plus 1, and our integration is actually integration x dx, so that means it is x to the power 1. So by integrating this, you will get x to the power 1 plus 1 divided by 1 plus 1, that means it will be x square by 2 that I wrote here. Okay, so what about this thing? This is called limit, and this limit, just for the timing, just forget about this limit and just put it here. Write down this x square by 2 within a bracket, and just write this limit here 0 to x. Now you have to do is that just put the upper limit, that means, okay, again 2 is a constant, so just bring it out, so that will be k by 2, and so there will be x square inside the bracket, and just put the upper limit, that means instead of x square you have to put x again, that means since it is x, so if you suppose you do have the 5 here, so that means instead of x you have to put this 5 here, that means you will get 5 square minus, again put the lower limit here, that means you will get a 0 square. Okay, so here I have the upper limit x, so that means my value will be, just by putting x here, x square minus, by again put the lower limit 0, you will get x square minus 0 square. So that will be EP equals to half of kx square. Why it is EP? It is the potential energy, since the kinetic energy, that means the amount of work done, that the amount of work done on the spring is actually stored inside the spring as the potential energy, and this kind of potential energy is called elastic potential energy. Reason? Because it is due to the change of its shape or size. Okay, so it is not the gravitational potential energy, it is actually elastic potential energy. Okay, so next topic of discussion is our work energy theorem. So here it is. So what is work energy theorem? So before briefing the statement, just do some calculation. So what is work done? Work done is your dw equals to f dot dx. Now here our assumption is F is applied force and that displaces the object by dx. This is also vector. So work done will be dw equals to f dot dx. Okay. So here I already wrote that, just sorry for that. I write down the same things here also. So net work done will be our, again I just discussed about the integration. When you know about something that is very small and you want to know about the same kind of variation on a large scale, you have to integrate that. So we know the amount of work done for a small displacement dx. Now we want to know the work done for a very large amount of displacement. We have to find the integration. So w equals to, that is the total work done, will be integration of f dot dx. Now f can be written as m into a is again vector dot dx. So a is our dv dt, that is the rate of change of velocity. V is our, again, velocity is again vector. So just use a little trick, just divide the dx with dt. That is not division actually, that's called chain rules. Okay, so just dx by dt and dt will be multiplied. So thing looks same. Now dx dt, that is dx is your displacement divided by time, that is your velocity, that is your v, and dv dt, just dt and dt you can cancel, and note that cancellation is not actually permissible. And so this is again chain rules, so you can cancel, but that will be in your mind. So this term is div, this term is your v, and this is dt will be, that will be dv, dt dt, that will cancel. So v dot dv. Now that is the v is the velocity and dv is the change in velocity. Okay. Oh, again, so dv must be here, v must be here, but I have just exchanged their positions. So it's simple because this is a scalar product, dot product. So we can write dv dot v as v dot dv. Okay. So v dot dv can be written as a dot v, can be written as ab cos theta. AB cos theta, a dot b can be written as ab cos theta. So dv can be, vd dot dv can be written as v db cos 0 degree. Why it is cos 0 degree? Since velocity and change in velocity must be in the same direction or in maybe in the opposite direction. Okay, so that must be okay. So just take the m, that is the constant term, out of the integration. V dv, again just you, now due to the application of force, let for this case the object was not at rest initially. The object has the velocity, had the velocity u, and now the object has the velocity v. So that means the object has the change in velocity from u to v. So now w will be your m, integration v dv. Now that shows the change of velocity that you have to integrate. That means you have to increase, and from where to where? The object had the velocity u initially, now object has the velocity v, so you have to integrate from u to v. Okay, so now again by using this equation, x to the power n dx is x to the power n plus 1 by n plus 1, that is your v to the power 1, that means it will be v square by 2, that means v to the power 1 plus 1 by 1 plus 1, that is v square by 2. Just put the limit here again, uv. Now 2, you can bring that out or you can leave it here also. So just put the values here, that will be your v square by 2 minus lower limit will be u square by 2. Just multiply that, half of mv square minus half of mv square, that is your final kinetic energy, that is your initial kinetic energy. So actually the statement of work energy theorem is work done on any object is exactly equal to the change in kinetic energy of the object. Okay, so that's the end of discussion, today's discussion. Thank you.